Yes, 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 I can hear you.
Perfect. We can now also hear you. Great. So, can you see PowerPoint now as well?
Yes, yes, I can see that.
Great. I think when we did the sound check, we were a bit closer to the mic, but just for a second then. Okay. Welcome everyone. Super nice. We did not know, I mean, it's a time series forecasting event. We had 100 people that signed up, but I think there are 30 to 35 in the live stream, and we didn't know if one person would appear or 100. So I'm really happy that actually the room is filled, not too full and not too empty. And welcome all of you online as well, but of course also here in Heidelberg for this second event actually regarding time series forecasting. And before I introduce our first speaker and Robert walks you through the agenda, I just wanted to summarize why we actually started with this. That's actually a picture I had for a presentation. It was a business presentation. Why actually AI and the consideration of using technology it's a good moment now, because everything changes fast, costs are exploding, and I mean the answer until okay, too many open programs probably. The answer until last year was Excel. So I mean that's probably hopefully all of this room are fighting against. I mean, there are a lot of tools below, but most of the things, I mean, we read papers, but most of the things, if you go to real life, people are really working quite basically. And I mean, when last year everything started with AI, I was pretty hyped, like, oh, okay, more people have AI budget, more people want to do actually AI. But after the hype comes reality. And I think all of our clients ask us, hey, yeah, can we just use ChatGPT to solve actually this problem that you just mentioned? And it was quite a tough year to actually, I mean, we will hear also something today about GenAI and time series forecasting, but to differentiate this first, as there's not one AI to actually solve all problems. And I mean, just an example here, doesn't matter who of you used it, probably already these hallucinations are everywhere. And we have a new example where we asked for a recommendation, and it just went into the documents, and it saw that in one document it says you should buy for 1,500 euros some stuff. So it was just a sentence in the document, and this was the recommendation that GenAI gave back to a business person, and really confident, right? And that's where we said, okay, actually there is probably not one AI to rule them all. Azul, looking forward for your talk and that you show me there is. But we actually say there are two buckets, right? There's this generative AI bucket and this forecast and recommendation AI bucket. And everyone is hyping the left side, but we think that on the right side, there's actually a lot of potential, especially if you look into business critical problems. And that was the reason why we said, okay, there are probably 100 GenAI meetups, and we want to do another kind of meetup. And that's why we started, I think, end of last year. With the first one, which was pretty cool, where we talked also about automated modeling, AutoML, but also how you can win time series forecasting competitions without a lot of AI and a lot of human intelligence. And today we will follow up on this and dive deep in one-time weather and one-time generative time series forecasting. But I think, Hubert, I just stole already part of your part.
That's already good. We are behind the schedule anyway, so stealing some of my parts is fine then, I guess. So basically also from my side, good to have you here, everybody. Good to have already Azul waiting in the queue. I just want to emphasize like how important this is to us for building also the community, especially for time series forecasting. Doing this the second time here in Heidelberg having like in total like 100 people signing up for this event. I mean, time series forecasting like one couple of years ago was not that cool. Okay, so nowadays we see like the urge that this is getting more and more important. It's getting more and more popular, and also businesses are more dependent by really good technology, machine learning technology, in order to do proper forecasting, probabilistic forecasting, all that stuff. So it's really cool having you all around here and having so good speakers here today to really cheer this topic and to really build a community around us, because it just helps steering businesses and make us all more effective. Let's jump quickly through the agenda. So we have Azul now talking about GenAI. Then we have some networking in between. Afterwards, we're going to listen to Dr. Sebastian Lerch, who's going to talk about probabilistic weather forecasting, so slightly different topic, but super interesting as well. And at the end, we finish off with some snacks and beverages. It's 8:30. We might be finished at around 9:30 or maybe later on, let's see. And then last but not least, okay, there's already we are super happy to announce already like a third edition of this meetup, because this community is just growing and growing, and it's super cool to see. And if you have also like an interesting topic that you want to share within this growing community, I would love to contact. If you would contact us, it would be super nice, so we can plan ahead. Here are some of the speakers of the first event. Super nice to see those faces, and let's add more faces as the more we do these meetups here in the future. And then last but not least, I wish you like all a great evening. Have lots of fun. I hope we gain more and learn a lot of insights regarding different topics. And I welcome then now the first speaker, Azul, who's talking about GenAI forecasting. And I would say, Azul, the stage is yours.
Thank you so much. Thank you very much for having me. I'm really excited to be here. I'm Azul. I'm CTO and co-founder of Nixtla, and in this talk we'll be talking about time series forecasting, and in particular in the generative AI space. Let me share my screen. So basically, to give you a little of context, we are Nixtla. We do time series forecasting research and deployment, and time series research is the systematic approach to unveil the future. And at Nixtla, we started creating a time series ecosystem, which is open source. We have different open source library specialized in different fields or subfields of the forecasting topic. For example, we have statistical models through stats forecast, but also we have more complicated models. For example, in the deep learning space, we have neural forecast, which basically is an open source library that has a lot of different neural forecasting methods, including some of the methods that we've been developing in the research side of Nixtla. And we are really excited because a lot of different companies have been used the Nixtlaverse, our open source ecosystem, in production. For example, Microsoft, Mozilla, AWS, Alando, among other companies. So we envision this Nixtlaverse, this open source time series ecosystem, to be really wide in the kind of things that you can do. For example, you can not also feed particular models for a small data set, but also we are really focused on making those libraries really efficient in the sense of computational complexity, and also to be capable of handling a lot of different data sets. For example, we have integration with Spark, Ray, and Dask for parallel processing and to handle huge amounts of time series data. So far, we have been downloaded like 10 million times the whole open source ecosystem, and we are really excited to be Nixtla, to see Nixtla being used in production environments. And in our path, we have seen that forecasting is extremely hard. In some cases, it is also confusing. And of course, it can be really expensive if the deployment is not really um, taken care of, right? So for example, to build a forecasting pipeline, you need to clean the data, you need to perform feature engineering. In particular, for example, if you are working with machine learning models, of course, you need to create lags or transformations of the lags, and to do a lot of feature engineering. Also, there are a lot of different models that you can use in the time series forecasting space. So basically, you need to select the best model or a combination of them. For example, assembling the models using cross-validation. And of course, this can be really computational expensive. And of course, you need to parallelize process in this sense for the pipeline to be really quick, right? And after that, once you have your best model and you are satisfied with the results of your model or your ensemble of models, you need to choose the right infrastructure. And after that, you need to deploy the model or a combination of the models. And after that, you need to monitor the deployment. So there are a lot of different steps in deploying forecasting models in production, and it can be really hard to maintain. So what is the solution? The solution comes from the idea behind LLMs, but applied to time series data. In particular, having foundational models for time series forecasting can enhance the way that we deploy these kind of models in production. So what is the main idea behind foundational models? At the end of the day, we are trying to fit a function with a particular set of features for the forecasting space. And of course, we want that model to provide not just point forecast in the sense that we are not just interested in a particular set of future values, but we are trying to estimate the whole distribution of the time series data. In this sense, for example, we are not only interested in the expected value of that conditional distribution, which is basically the distribution of the time series given the past values of the time series, and also exogenous variables that can be, of course, continuous or categorical, right? And we are interested in estimating the whole distribution. In that way, we can have not just point forecast, but also prediction intervals. And the prediction intervals are really important in the forecasting space because, as you know, we can take better decisions, minimizing, for example, the expected value of the different scenarios in the future. And basically, this opens the door to talk about foundational models, which is basically a pre-trained model on an usually really large source data set. And basically, the idea is that once you have your pre-trained model on a huge source data set, then you can apply that pre-trained model to a new forecasting task. And the main idea is that you don't need to train the model on that target time series. The model can make inference on any new time series, and that's the main idea behind foundational models. And we think this idea is beautiful because also share some interesting relationships with the LLM space, right? So it is the main idea as in large language models, but instead of using text data in a foundational time series forecasting model, you are using time series data, which is basically the main difference between these two worlds. And basically, also we have this definition because at the end of the day, it's really important to know, at least theoretically, if the pre-trained model can generalize to new time series datasets. So basically, in a paper, we we are proposing this measure that basically gives you the distance between a particular time series and another time series. And the main idea behind this definition is that you can have different data sets of time series data, and then you have the option to compare them. And the idea behind this is that since deep learning models in the forecasting space take windows of the time series of size, input size, and output size, and the distance basically compares all the windows of the time series against the other windows of another time series. And that basically you can have a measure of the distance between the time series. And that's why we published and we released TimeGPT-1, which is the first foundational model for time series forecasting. And in this space, generative AI allows us to not only show the results of the TimeGPT-1 model, but also expose it as an API. I will talk about that a little bit later. So this was the first foundational model for time series data, and we trained that model on more than 100 billion of data points from different domains. And this is really important because at the end of the day, we need different time series. And one thing that we have seen in the empirical results is that it is more important to have a wide set of different domains or different sources than the number of data points. Like it is a combination between the amount of data you have and also the diversity of the data that you are training the model with. This is the architecture of TimeGPT-1. We basically have a lot of different sources ranging from finance, electricity, web traffic, retail, tourism, IoT, healthcare, transport, economics. And we feed a transformer-based architecture with that huge data set. And basically, once the model is trained, we can make inference on new sources of data. And TimeGPT-1 supports multivariate forecasting. Also, since we are really interested in the whole distribution of the forecast, it also supports prediction intervals. It also supports fine-tuning. For example, if you want to update the weights of the model based on your own time series data, you can use the fine-tuning feature. And also it supports anomaly detection. And that is the main idea behind the inference part of the pipeline. You have a target variable that you want to predict, and basically you pass that time series data to the pre-trained architecture, and the final results are the forecasts for the future. TimeGPT-1 offers accurate predictions. It is also orders of magnitude faster. And as I mentioned before, it is also fine-tunable in custom layer. And I think this is the most important question regarding TimeGPT-1, and it is how does TimeGPT-1 compare against, for example, the statistical models, machine learning models, deep learning models? How does TimeGPT-1 compare against, for example, AutoML solutions out there? And one other important question is, there are other foundational models for time series forecasting, and is there an advantage of TimeGPT-1 against those other foundational models? And I think those are the really important questions, because at the end of the day, if generative AI works for time series data, we need to be able to answer those questions. In the sense that, for example, if a statistical model is better than a pre-trained transformer, even if it is more complicated, at the end of the day, for practical applications, it would be better to have that statistical model. So I think these are the right and the important questions to ask regarding generative AI. And I think this is also important because at Nixtla, we deeply believe in benchmarks. Uh, all, all of our implementations in the open source ecosystem are fully tested and fully benchmarked. For example, if we are releasing a new statistical model, a new implementation, for example, of an old classical statistical model such as TBATS or ETS or the theta method, we are really aware that we need to benchmark those implementations against other implementations and also against really basic benchmarks. For example, the naive method, which basically the forecast produced by that method is the last value of the time series, or the seasonal naive method, which basically repeats the last seasonal period of the time series. So it is really important in practice to have different benchmarks and to compare our solution and the deployed solution or the final solution against those benchmarks. So we did that, and this is the first results that we have seen in different data frequencies. And we compared TimeGPT-1 with zero-shot inference in different series, more than 300,000 time series. And we compared them against different statistical models, different machine learning models, and different deep learning models, which is really what is really important in this table is that all of the models that you can see here were being trained in the time series. So basically, the only model that produced zero-shot inference is TimeGPT. This means that TimeGPT-1 didn't see the time series in this evaluation at training time. So it's basically zero-shot inference. And as you can see, in the monthly and weekly frequencies, TimeGPT-1 has better performance than a lot of different benchmarks. Here, the results are weighted by the performance of the seasonal naive model. As you can see, seasonal naive has one as in the whole in all the columns, and TimeGPT outperforms those models. We have also the theta method, the dynamic optimized theta method, the ETS, complex exponential smoothing, ADIDA, IMAPAN, Crosstown Classic, among others. In the machine learning space, we trained LGBM, and also we included deep learning models such as LSTM, DeepAR, TFT, and NFIT. And of course, to produce this table, we used the Nixtla version. For the statistical and benchmarking models, we used stats forecast. For IGBM, we used ML forecast, and for the deep learning models, we used neural forecast. Also, in the daily and hourly frequencies, which are which are in these two columns, we have seen that LightGBM, for example, in hourly data has better performance than TimeGPT. Even considering that, TimeGPT has a really good performance on those particular tasks. This means that we need to improve the data pipeline to include more daily and hourly data in future iterations, and also improve the architecture of the model. So this is the comparison against statistical, machine learning, and deep learning models. So the first question is TimeGPT is better than those classical models. So the next question is, how does TimeGPT compare against some AutoML solutions? So basically, we compare TimeGPT against Azure AutoML. in different time series tasks. We included hourly, daily, weekly, and monthly frequencies, just as in the previous table. And we have seen that TimeGPT is 12% more accurate in terms of May and RMSE, and it is 300 times faster. And it is really interesting because at the end of the day, Azure AutoML fits different models, statistical ones, machine learning ones, even deep learning ones, and then uses a particular way of ensembling them to have the best result, and uses cross-validation to see which model performs better in a particular time series. So it is a complex pipeline to run Azure ML. Maybe I can share the experiments part. Basically, we have different experiments. All of the experiments are open source. Here, for example, you can see the Azure AutoML comparison, and I wanted to show you the code behind Azure AutoML, because at the end of the day, it's an AutoML solution, but it is a little bit complicated to use it because it requires a lot of different steps, the steps that we discussed earlier in the presentation. So basically, you need to have an Azure AutoML handler that basically gives you all the required code for sending the task to a particular cluster. So you need to have a train component, an inference component, and you need to set up a lot of different things for the cluster to work, and also save the forecast, save the ID of the job for to later to retrieve the forecast once they are ready. So you need to do a lot of different things. For example, here to download the forecast, you also need to check if the forecast is ready or not. And also you need to save the jobs to request the forecast later. And you need to create this cluster, and you need to set up infrastructure, and you need to manage credentials. So it's a lot of different tasks that you need to perform in order to run different AutoML solutions, in particular our Azure AutoML. And the beauty behind TimeGPT is that in just a couple of lines of code, you can have really good forecast in a smaller time. So basically, you just need to write like 20 lines of code for TimeGPT to work, and with that you will have better performance. Sorry, sorry about it. And with that, you will have better performance that a lot of different AutoML solutions out there. So that's the main idea behind this table, that with TimeGPT you can perform better forecasts in a smaller time, and at the end you will have forecast that outperform some AutoML solutions. And the final question is are there other foundational models for time series forecasting? And the answer is yes. There are different foundational models in this space. A lot of them don't share the code yet, but we play around with Black Llama, which is an interesting foundational models because they released the weights, and also they released the collab notebook on how to use that public weights and generate some new forecasts. And I think that was incredible because they released and made open source the weights and all of the code, and it was really amazing to see that out there. So basically, we compared lag llama against seasonal life, which is a really easy to implement and easy to use model. And we benchmarked those models against different data sets. Here, for example, we have the M competitions, which are really important competitions in the forecasting space. And which is really interesting about these data sets is that they have different frequencies. For example, we have M1 monthly, M1 quarterly, and also we have low frequency or high frequency time series, for example, M4 hourly, among others. And also we benchmarked, we used in this experiment a tourism dataset, which is also widely used in the research arena of the forecasting field. And these datasets were not included or evaluated in the original lag llama paper, so we included them. And as you can see, in terms of maize and MAPE, seasonal life has better performance than lag llama. And in terms of CRPS, which evaluates not just point forecast, but also the distribution of the forecast or the prediction intervals of the forecast, seasonal life has better performance. In terms of time, also seasonal life is 1,000 times faster than lag llama. And lag llama is based on transformers as well, and this benchmark encompass more than 100,000 unique time series. And this is really important because in the original lag llama study, they only used 3,000 time series for testing the model. And as you can see in the data sets that they evaluated, lag llama has better performance in terms of CRPS and also in terms of MACE. So we think this story complements the paper of lag llama, right? And of course, for the seasonal life, we use the stats forecast, which is part of the Nixtla, and also this experiment can be fully reproduced in our experiments folder of the Nixtla repository. So basically, here you can see how we implemented the lag llama pipeline, which is basically really straightforward. Basically, we downloaded the weights, and then we used the Colab notebook that they provided, and we implemented here. And also you can see the stats forecast pipeline, which is really easy to read and implement. Basically, you have to code like 5 or 10 lines of code. We also here, this is not included in the presentation, but also we did a comparison against Prophet, and the results are basically the same. TimeGPT has better performance and a lot of different sources of data than Prophet and than seasonal life. And we have a lot of different things that we are working on right now. For example, we are trying to build this bridge between LLMs and foundational models for time series forecasting. And one of the first efforts to do that was TimeLLM, which is a published paper. And basically, we included TimeLLM in our neural forecast library. TimeLLM is interesting because it combines a pre-trained large language model with a particular architecture for time series forecasting. So basically, the LLM is trying to infer different shapes of the time series data based on statistical metrics of the data, for example, mean, standard deviation, and so on. And the prompt of the LLM is that set of time series features and the particular output that we want to have. And also, we are working on implement Momento in neural forecast, which is another foundational model. So we are really excited to include that that model as well. And with MGPT-1, you don't need machine learning expertise, which is really exciting. I would say about MGPT-1 is that it is the first foundational model, but also it is the only foundational model available through an API for time series forecasting. And basically, let me share this stuff instead. Basically, you can access that model through an API. For example, if you are working not in Python, but I don't know, in Node, because you are building an application that shows the forecast of the sales in real time, or in a web application, you can use TimeGPT. You can access that complex architecture and the complex pipeline for training and deployment for serve those forecasts. And for example, I don't know, if you have instead PHP or Ruby, you can have the forecasts. And as you can see, the request takes the forecasts are being generated almost immediately. For example, I don't know, if you have Ruby, you can try it, and I think the API is incorrect here, but you get the idea. And also, you can use our Python SDK that basically allows you to interact with the API, but using a common used programming language, namely Python. And basically, instead of parsing your data and upload it as a JSON, you can basically just send the pandas data frame that you have, and immediately just calling the forecast method on that pandas data frame, you will have you will have the forecast in the same format as a pandas data frame. And you can play around with different features that TimeGPT-1 has. For example, here you can see how TimeGPT detects anomalies. For example, here we are seeing an electricity data set, and basically the anomalies are being detected here. Also, you can produce quantile forecasts, not just prediction intervals, but if, for example, if you want to predict a particular percentile, I don't know, let's say 90%, you can use TimeGPT to do that. And of course, you can use fine tuning. We recently added this option. For example, if you are interested in reducing the MAE instead of RMSE, you can use the fine tune dose to specify, oh, I want to reduce the MAE. The fine tune steps that you want the model weights to be updated. And with that, you will have like a fine-tuned version on your own data of TimeGPT-1. And also you can include exogenous variables, which is really amazing because in a lot of different scenarios, there are external factors that affect the forecast. I don't know, for example, holidays or special days, even the price of the forecast, the price of the sales if you are doing sales forecast. So basically, you can include those exogenous variables as well. And here, for example, the SDK contains a particular model for including holidays and special days, and also you can see the weights or the importance of those exogenous variables of those holidays. And yeah, for example, here, this New Year's Day for this data set is really important, but also the National Independence Day. So you have like a kind of explainability thing behind the exogenous variables. And of course, you can use cross validation to test the performance of TimeGPT. Currently, we have two versions of TimeGPT-1, namely TimeGPT-1 for short tasks and horizons, and one for long horizons tasks. And which is also important to notice here is that the SDK works out of the box with Spark. Currently, the main limitation behind the SDK is the latency of the network. For example, if the network is too slow, if the data is too big, so probably you will have problems, because at the end of the day, the data needs to uh, to go through the network. But of course, if you have a huge amount of data, you can use a cluster on Spark and build a Spark data frame. And with that Spark data frame, you can feed TimeGPT. So basically, the request will be handled concurrently in this case. And the main idea behind that is, it doesn't matter if your data is huge, you can still use TimeGPT for that. And so that's the main idea behind TimeGPT, that you can produce accurate forecasts without deploying a whole pipeline. And of course, if you want to try out TimeGPT 1, please join the beta program at this URL, and we can give you early access, and we can give you a certain amount of dollars to try it out. Right now, we are eager to have more feedback and to learn more about the capabilities of the foundational models for time series forecasting. So if you are interested in trying and playing with TimeGPT, that would be really good for us, and also I think for the field, because we are trying to see what are the boundaries of the foundational models, what in what specific cases we need to put our attention to keep improving the model. And that's basically it from my side. Thank you, sir. Thank you very much. I don't know if you have any questions or comments. Thank you so much, and happy forecasting.
Thank you. Hi Azul, thank you for the great presentation. My name is Nicolas, and the question is not that technical. I just want to know how the release of Llama impacted on you guys. Like, did it drop the amount of users that were interested, uh, or yeah, or the amount of clients you could get? And yeah, in that would be my question. And also, I sign up for the beta, so I would be very happy if I can get in. But yeah, that was my question. Thank you.
Thank you, Nicolas. Yeah, sure. We can give you access, absolutely. And regarding the Lag Llama release, we were really excited, because at the end of the day, we think that as a field, we are going in the right direction by building and publishing foundational models for time series. And yeah, it also was like really good opportunity for us to see that a lot of different people is also working on this topic. So basically, for us, it was really exciting to see. Oh my God, we are seeing TimeGPT one uh, alternatives. So it was really cool for us. And also, we deeply believe in collaboration and benchmarking. So at the end of the day, we are not like fighting or something like that against like other teams or something. But we want to keep improving our product. And so basically, I don't know if in the next weeks there is a new foundational model that has better performance than TimeGPT that would also be good for us, because at the end of the day, those experiments and those approaches will help us to improve TimeGPT. And at the end of the day, I think that's the main idea behind Nixtla and behind science and behind the things that we are doing, that keep improving the things that we already have. Yeah, that would be my answer. Thank you. Thank you so much.
Thank you. Do I have time to do another question?
Go ahead.
When you trained the model, you said that you took data from many branches. Did you tell the model when you give it as an input, like this data comes from this branch and this other one from this other branch, or does it already generalize well without knowing what type of industry the data comes from?
That's a really good question. Yeah, in the first iteration, we didn't include the source of the data or the domain of the data, but we are iterating on that. And yeah, we are thinking about including that metadata features or information in TimeGPT-2, which will be the next version of the model. Yeah.
Thank you.
I go really quick. Thank you, Azul, for a great talk. I'm Johannes. It's amazing to adapt this idea of foundation models also to time series. And I wished I would have known of you guys 6 weeks ago. That would have saved me a lot of pain. Probably. I was playing with Prophet, and yeah, you know the drill. I would be interested in learning about how do you even train a foundation model. You mentioned some 100 billion data points, and of course everyone here probably, or most of us, have trained the model already, and you're like, okay, now the weights are changing again, and you're like, how can I make this kind of resilient to really create a foundational model?
Yeah, that's a really good question as well. Basically, we have a pipeline that uh, tries to find the best hyperparameters using cross validation. And what you mentioned is really important for us, like the results to be generalizable to another task. So at the end of the day, we have this pipeline that considers a specific series as validation set, and then we explore these hyperparameters using a cluster of GPUs to make the training time as low as possible. And then once we have the best hyperparameters, we test in another set of time series to see if they are if the results are general enough. Yeah, but this is really important for us. And also there are some technical details, for example, handling the data and normalizing it, because if there are outliers in some cases, the model can show results that are not really good. And yeah, we have to do a lot of cleaning as well in the series to see if they have different different values or different scales. And yeah, it involves a lot of research, and in the infrastructure side there were also things that were not so easy to implement, but And one thing that I wanted to share with you is that we at the beginning we weren't sure that foundational model for time series forecasting could exist. Like we were really really amazed to see the results. It was really like empirical. We had this idea and um, we said, let's see what happens. Let's build this and see what happens. And we were really really amazed to see the results. Like it was like an aha moment. Oh my God, this is working! I can't believe this. Yeah.
Always on and off. Sorry for that live stream. Go ahead.
Thanks for the great talk, Florian and Paretos. One question I had is, you said there were two models, one for short horizon and one for long horizon. What made you go down that path of splitting up or of taking two models to the problem, one for long and one for short horizon?
That's also a really good question. Yeah, so at the end of the day, for the models that we are training, of course you need to specify the horizon of the task, no? So at the end of the day, you can specialize a particular model for a specific horizons. So, and in the first version of TimeGPT 1, we train it the model on short horizons. So basically, the model is specialized in those horizons. And after some testing, we started to see that as long as the horizon increased, the performance of the model decreased. So we decided to include this particular version for long horizon, now trained on longer horizon. So basically, the model is specialized on that kind of horizon, and this is important because, for example, highly time series with high frequency. I don't know, for example, minutely or hourly. It is really important to have a huge horizon. So yeah, we trained in particular the model for that specific task.
It seems like the sequence is all what you need. And my question, how did you find the data for training? How did you sample them?
Yeah, so basically, that is like our secret sauce, a little bit, the data part, and yeah, right now the data is private, and also the way that we obtained the data and the source that we sampled them from. But we are working on releasing some parts of the data and also the process, and also in the future, yes, we envision like this option to have the complete data open source and available to everyone, but right now it is private. Yeah.
I want to use time GPT. Which data set do I need? How big? And which infrastructure to run your model?
So basically, you don't need a particular amount of data to use TimeGPT. I don't know if, for example, in your use case, you only have I don't know 100 time series. You can still using TimeGPT. If you want to improve the performance of the model and also to improve the forecast, you need to have more data. But also we have seen that for small data sets with with a large number of timestamps, the fine-tuning feature works really well. And also if the fine-tune steps is big. And yeah, so you don't need a particular amount of data. If you have more, that's better for the model. And regarding like computational characteristics or the computational specifics of the infrastructure, for example, let me this benchmark. We ran this benchmark against Azure AutoML using a MacBook Air with 8 CPUs and 8 gigabytes of RAM. So basically, since the model lives in a particular infrastructure, you don't require a huge computer to make the request. You only need to worry about the size of the data, in the sense that it needs to to be able to fit in the RAM. But as long you have enough RAM to download and use your data, you can use TimeGPT without problems. Having said that, we also have like this enterprise version of TimeGPT, and basically we can share with you, for example, a Docker image of the model, and then you can choose your own infrastructure to deploy the model. I don't know, for example, you have questions or you are worried about like the data to go through the network, you can use the self-hosted version of TimeGPT, and you can use your own infrastructure to run the model. We also have that option.
Robert here again. As Fabio said, pizza is already getting a bit cold, but I have this one question on my mind that I definitely wanted to hear your opinion on. So for me, like the biggest difference between like a foundational language model, namely an LLM, and like a foundation time series model is like the dimensionality, which is like for the language models, like most of the time it says like one dimension and it's fixed and it's language, right? And you can easily generalize it. For time series models, we have a lot of times it is impacted by exogenous variables, exogenous factors, which are not so easy to generalize across various industries, right? So do you see like a limitation regarding foundational models regarding this issue, and how do you cope with this, since you also trained on lots of different data sets that I would say also have like are impacted by exogenous factors? So how do you cope with this issue regarding your foundational approaches?
Yeah, I think this question is amazing, because yeah, there is a lot of the future involved in that question, because I share with you those point of views, right? Yes, time series is really complex, because what you mentioned, like you have a lot of external factors influencing like the target variable you want to predict, and I think in the future, and that's something that we have seen, but we don't have yet enough evidence, is that it is more important the diversity of the data rather than the amount of data points that you have. And also it is really important to consider those external factors while training. Of course, there is the limitation that we don't control, and we can't understand completely what are all the factors that influence a particular target variable. But as long as you have enough knowledge of the process that you are trying to model, and the factors that in some ways affect the process, and you include that data, and the data is diverse enough, I think that will improve the the forecast, right? And yeah, and it is also really important to have the right architecture to handle those things. Um, and yeah, because it, the data is really important, but also the architecture. So I hope to see a lot of effort also in the architecture space. For example, how to handle different frequencies, how to include the domain of the time series, how to include knowledge based information. For example, I know that this time series comes from this particular subfield, or I don't know. I know that outlier was created by a particular process that I only have the information. So we need to find a way to include that information that the person has in the training process, and then in the inference time. So I think it's really exciting this time that we are living on, because yeah, there are a lot of things to do in the space. So yeah, it's really exciting. Let's see what happens.
Thank you very much.
Thank you, Azul. Big shout out again to the US and for waking up early. Thank you. And I mean, the next talk is about external factors and weather, as everyone is like the number one requested feature. So really excited. But first of all, thanks Hank for keeping the pizza warm. So feel home. There are drinks in the fridge over there. We do now a 40-minute break, and at 8:10, we will continue with our second talk.
Thank you. Bye bye. Nice to see you.
Nice. Ja, das schon.
Ich turn schon mal das Mikrofon hoch. So we're getting the last things up, and then we're getting started. Okay, last people. Grabbing some water. Perfect. So let's come to our second talk. We have Sebastian here. Thanks a lot. Perfect gateway before from Robert's question regarding external factors and that they are hard to be included in the right way to make a difference. So I'm really excited to have you here. For one reason, it's really cool, especially also for the Rhein-Neckar region, to have people from the region presenting things and to see also what happens in Karlsruhe, but also here on the mountain in Heidelberg, and which research you are driving. So please welcome Sebastian with a warm applause, and then the stage is yours.
Okay, thank you very much for the invitation, for the kind welcome. So I'm Sebastian. I'm a junior group leader at KIT. That's my group, so some postdocs, PhD students. And today I would like to give a bit of an overview about our work and about weather forecasting and the role of AI in weather forecasting today, a bit more generally. So, to start, why do we care about the weather? It's, from a business perspective, maybe an external factor that's interesting for many purposes. Weather is also interesting for maybe our personal lives when it comes to deciding if I want to come here, do I take a bike or do I take a bus or do I take a car? But maybe more importantly, on a broader scale for our society, I also think that weather is very important, in particular in light of a changing climate. Thinking about things like a transition towards renewable energies, where weather forecasts will become maybe more important for us than they have ever been before, or thinking about extreme weather events, which may become more frequent and more extreme, requiring accurate and reliable warnings. So my talk will have sort of three parts. I'll start by telling you a bit where weather forecasts come from now, and then I will talk about two ways of using AI in this weather forecasting process. First one is maybe more what we are currently working on, called a process called post-processing. And then in the end, I'll talk a bit about purely AI-based weather models, which has come up in the past 1 or 2 years or so. But as of today, whenever you consume a weather forecast on your favorite app or website, this will usually be based on a physics-based weather model, so-called numerical weather prediction model, where atmospheric processes are modeled via systems of partial differential equations, discretized in time and discretized in space, so on a three-dimensional grid around the globe, which you can see here in the illustration on the left-hand side. And these grid boxes are, in the highest resolved models today, are something like 10 by 10 kilometers in size. Now, these models, these differential equations are then solved on supercomputers by weather services, on some of the largest supercomputers in the world, in fact, because this, of course, requires tremendous computational resources. And there are many sources of uncertainties in this process. Most importantly, maybe the initial conditions, because, of course, we do not observe the weather everywhere perfectly on this 3D grid. And there are errors in the models because lots of the processes, things like radiation processes or processes in clouds, have been below the resolvable scale of the model, so they have to be put into the model somehow indirectly, and there are errors in this process. Which is why most weather services today don't run just a single model, they produce what is called an ensemble forecast. So, for example, by randomly perturbing the initial conditions, they run the same model forward over time, which leads to different potential scenarios for the future development of the weather, from which we can just compute probabilistic forecasts. For example, the probability of rain here over the UK by just counting in how many of these simulations do we observe rainfall at a specific grid point. Now, that's great, and ensemble forecasts are great as a tool today. However, there's a problem. because despite continued improvements, these forecasts show systematic errors. And I brought you two examples to illustrate this. So these are both forecasts of temperature at Frankfurt Airport. And those forecasts were made always 2 days in advance. You can see like a couple of weeks of forecasts here. So the forecasts come from the ECMWF, which is the European Center for Medium-Range Weather Forecasting, which runs arguably one of the most advanced forecasting models in the world. The forecasts are here these 50 gray lines, that's the ensemble produced by ECMWF, and the red line are the corresponding observations, and you immediately see that there is a problem here, because the forecasts are too low by something like 2 to 4 degrees Celsius, which means they are not really useful for an operator at Frankfurt Airport who will be interested in, for example, the probability of freezing on the runway, which here will be drastically overestimated by the forecast. Second example from the same data set, I just picked a different time series here. So here you can see that there's not really a consistent bias here in November 2016, but you can see a different problem, which is that the uncertainty in the ensemble forecast is too small. So the red line of the observation always lands outside this uncertainty band provided by the ensemble forecast, so the physical model underestimates the true uncertainty. And this is now where AI comes in, or one of the ways of using AI comes in, or statistics, and what we do via a process called post-processing. So the basic aim of post-processing is to fit a statistical or a machine learning model on top of the physical model. So our post-processing model takes forecasts from the physical model as input, and then produces a probabilistic forecast as its own output. Of course, with the aim of, in this process, correcting systematic errors, such as the ones you saw before. So we call this also a distributional regression model, because everything that we do is probabilistic, so the output will always be some representation of a probability distribution. Now, this idea is not new. We used this already 20 years ago. First, models were classical statistical models, also called EMOS, or ensemble model output statistics models, where you can see here an example for temperature forecasting, where so the input are forecasts of temperature from the physical ensemble forecasting model, and then the output takes the form of a Gaussian forecast distribution, which has two parameters, a location parameter mu, a scale parameter sigma, and these parameters are now linked to the ensemble forecast from the physical model. For example, as you can see it's done here, so the location parameter is a linear function in the ensemble mean, the scale parameter is a linear function in the ensemble standard deviation, and then by estimating these coefficients A, B, C, and D from training data, this allows to correct errors such as the ones you saw before for future forecasts. This is all done by optimizing the CRPS, which also appeared in the previous talks, so some loss function, specifically for distribution forecasts and scalar real-valued outcomes. We can also phrase this a bit more generally if we want. So this essentially is what we call a parametric distributional regression model. So we want to model the distribution of a target variable y given some input predictors x. And we do this by assuming a parametric model, this f theta, for the target variable. And then the distribution parameters theta have to be connected to our input predictors via having to choose a link function h. And this already indicates sort of the problem in doing this, because of course our physics-based model doesn't just produce forecasts of temperature, but also forecasts of wind speed, of rainfall, of pressure, of humidity, and so on. So we have lots of different predictors available, but if we want to follow this statistical modeling approach, this would mean that we have to pick ourselves how the distribution parameters should be linked to all the different input predictors, which becomes very difficult if we have many of those. So I just told you this, and one way out of this problem is to use machine learning. Specifically, together with Stefan Rass, some time ago, we proposed to use a neural network model for this purpose. So we stay in exactly the same framework, but we now estimate the distribution parameters directly as the output of a neural network. This allows us to use arbitrary inputs, whatever we want, and the neural network takes over the role of this link function h and learns itself how to link the input predictors and the distribution parameters. So we can learn nonlinear relations in a data-driven way. I'll show you in a second that we can also use some tricks to have one model for many locations that's still locally adaptive, and to some extent also gain meteorological insight from the models. To explain this in a bit more detail, I have one example of a data set of a typical data set of the data sets that we work with. So there's also the data set that I used before. I just showed you Frankfurt Airport Station here. In fact, you can see that we have something like 500 stations over Germany. We have 10 years of forecasts and observations. Forecasts come from the seasonal death model I mentioned earlier. And here we have something like 18 variables. We interpolate them to the station locations, compute mean and standard deviation of the ensemble forecasts, and then we use 1 year as test data set and 9 years for training. And that's the type of neural network models that we proposed in this paper. So essentially, this is a very straightforward, fully connected feed-forward neural network, but as the output, we obtain distribution parameters of a Gaussian forecast distribution for modeling temperatures. And now, as an input, we can use different kinds of features. So shown in yellow here are the input predictors from the physics-based model. So we have interpolated to the station locations, we have forecasts of 18 different variables, and we use those as inputs. Then we have information about the station, things like coordinates or altitude of the station. And what we want to do is we want to estimate one single model jointly for all locations, but of course the properties of these different locations can be very different. Maybe very different if we have a station at Frankfurt Airport to a station up on a mountain or at the coast of the North Sea in the north of Germany. So what we do is we use a technique called embeddings that many of you will likely be familiar, that comes from natural language processing, where we essentially here use the embeddings to map the categorical feature ID, or station ID, to a vector of latent features, then used as additional inputs in the model. And by learning these embeddings jointly with everything else, this allows to generate local adaptivity in a model that's trained for all locations at the same time. And training happens by, again, CRPS occurs by using the CRPS as loss function to estimate all the weights in the network. And this works. So going back to the example I showed before, what I've done here is I've now produced a post-processed ensemble by drawing quantiles from the forecast distribution. And you can see that here in this example, the bias is removed and the variance is increased, so that now the red line of the observations typically lands somewhere inside this uncertainty band provided by the ensemble forecast. So this works for these two examples, but this also works, of course, more generally. So there are many more like quantitative details in the paper if you want to have a detailed look at this. But here again are the station locations, and I just color-coded the stations whether our model performs best or any benchmark model performs best. Benchmark model here also includes other machine learning models for this post-processing step, things like random forest models, for example. So these models work well. We get more accurate predictions, mostly because we learn, we can use different predictors. We learn nonlinear relations in a data-driven automated way. And a nice thing about this is that this actually can be used as a starting point for many different extensions. And I just want to mention two examples here, what we have been working on. So that's one paper with one of the PhD students in my group. And here we have been looking at ways to get away from this parametric assumption on the forecast distribution. Because thus far we are still assuming that our forecast distribution follows some sort of parametric form. And here we wanted to develop a model for wind gusts. So wind gusts are some sort of short-term maximum wind speed values, where it's not so clear which parametric model actually fits the data really well. So what we did is we looked at alternatives. For example, in the middle you can see we used a more sort of semi-parametric approximation to the forecast distribution, where we model the quantile function as a mixture of Bernstein basis polynomials, or you could do this even more non-parametrically by modeling the forecast density as a histogram and then just estimating the wind probabilities, all as the output of a neural network. And again, that's a map of Germany with stations that measure wind gusts over Germany, and you can see that first you can see that at most of the stations the neural network models perform best, so all the green symbols are neural network-based models, but you can also see that sometimes it helps to actually deviate from this parametric assumption, so different point shapes indicate different types of models. So we are working a lot with meteorologists at KIT and at weather services, and for them it's also very important to try to better understand what these models have actually learned. So they are in particular interested in seeing if these models pick up some sort of physical properties or physical processes in the atmosphere that are known. So we also usually tend to look at things like feature importance. So here it's again for this wind gust paper I mentioned, and what you see plotted is feature importances of different input predictors over the time of day. And I just want to highlight two things here, which are this gray line and the yellow line. So the gray line is the day of the year information that enters the model as an input, and you can see that this, or you probably can't see, I can see because I'm standing close enough, but what you could see if you were close enough, you could see that the day of the year information tends to be really important during the morning hours and during the evening hours, so when the sun rises and the sun sets, which is what changes over the course of the year. So that somehow the model has picked up that this is some important information, specifically during these times. And then the yellow curve is some sort of complicated variable that measures how much radiation arrives at the surface of the Earth. And you can see that there's a huge spike in the evening hours shortly before the sun would set. And this can actually be connected to some of the processes that cause these wind gusts in the atmosphere, called the evening transitions, and the meteorologists were very excited when we showed them these plots because they can explain this from physical knowledge and process understanding. So that's cool to see that the models actually learn something that corresponds to some of the expectations of the people who know the physics. We've also been looking at different time scales. So here you can see this is a global post-processing model, and we are looking here at the time scale that's called the sub-seasonal to seasonal time scale, so a couple of weeks in advance, which is very important for many applications, for example, for energy applications, where, for example, operators of a wind farm may want to know when there is low wind energy expected so that they can schedule maintenance during these hours or these periods of time. And here we use sort of UNet models to get forecasts that are probabilistic, of course, but on a global scale. So with this, I would like to sort of conclude this first part, and I'll talk about something quite different, which is a more recent development. Because over the past few years, there has been a new paradigm which has been arising in weather prediction, and people have, of course, with the rise of AI and machine learning, lots of different applications, been asking themselves, do we actually need all this physics-based models? Can't we just do this with AI? And in principle, why not, right? So you have an input data set on a grid, and what you want to do is you want to predict the transition to the next time step. You could do this with a physics-based model, solving complicated differential equations, or you could just learn a new network to do this. And there's lots of past data now available, so why not do this? Potential benefits of this are, of course, well, maybe we get better forecasts out of this. Maybe, at the very least, if we are not better overall, maybe we at least get good forecasts where physics-based models fail. So at timescales or in locations where these physics models don't work. Or maybe at the very least, we get equal or better forecasts at much lower computational costs. So once we have trained a new network to make a forecast, we just have to do one forward pass in every time step instead of solving all these different equations on a supercomputer. So we can do this on the laptop and don't need a supercomputer anymore. And if the next slide, yeah. Oh, sorry. But now I wanted to ask you, so what do you think? Can AI weather models, as of today, beat the physics-based models? So we can do a short show of hands. Who believes in physics? Who believes physics models can still do better?
Depends on maybe accuracy or computing time.
Yes, you're asking you. Not computing time, just accuracy for now.
Just accuracy.
Just forecast quality.
Physics-based.
Okay. Who believes in AI? Surprisingly few people. It's actually very interesting to ask this question in different audiences, but people tend to be skeptical towards AI. But you also saw that, well, the answer is maybe, so sort of all of you are right, or all of you are wrong. And I will explain why I put the maybe here. So, and to do this, I would like to start with a short history of AI-based data-driven weather prediction. History is in quotation marks because, well, the history starts like 5-6 years ago, when the first papers on this were published. So people tried this, as I said, 5-6 years ago, but this didn't really work. So this was more like a general proof of concept. You could achieve forecast skill with these AI models that were maybe similar to very simple toy models, so physics-based model that you can run on a laptop. So there was progress over the next years then, but the forecast skill was always very far behind any sort of state-of-the-art physics-based model. And just 3 years ago, there was a sort of a widespread consensus that this is going to stay this way. So very popular meteorologists went on record and wrote in their papers that like within the next decade, this won't happen. So data-driven models will stay far behind. But this turned out to be a pretty bad prediction, because then there have been some unprecedented, surprising developments since the last 2 years, essentially. And in a short series of couple of months, starting with the ForecastNet model and then many other models, a series of papers, or back then preprints, now partly papers at least, have been coming out. And you can see that if you look at the groups of authors, these are typically many people, and they all come from big tech companies. So people from NVIDIA, Huawei, Google, DeepMind, Microsoft Research have started to work on AI-based weather models, and quite successfully, as I will show in a second. And I've stopped here somehow in summer 2023, but the pace has even picked up, and every couple of weeks there's a new model that does everything better than any of the other models before. So there are two sort of strands of model. One is using transformers, and one is using graph neural networks, and both of them work more or less equally well. And this sort of AI revolution of weather prediction has also made its way into public newspaper articles. So here, most of those are in German, so sorry to those who don't speak German, but you can see that even like the Tagesschau is now reporting on AI-based weather forecasting. So what all these models have in common is that they work really well. So they reach or even surpass partly the performance of state-of-the-art physical weather models. They have like better forecasts overall if you average over lots of time steps, over lots of grid cells, but they also have better forecasts of individual events. And as you would expect, producing forecasts is much faster and thus cheaper. So here are some examples from the Pengu Weather paper from Huawei. So this is RMSE for two variables. AI forecasts are in red. Physics-based forecasts are in blue. Black is another AI model, but you can see here that the forecasts are actually better than the physics-based model. This is one of the state-of-the-art physics-based models, also again run by ECNW. And they also show some forecasts for cyclone tracks. So here again, forecasts by the AI model are shown in red. Blue is the forecast of the physical model, and black here is the true cyclone track. And you can see that the physical model makes some quite bad mistakes here at times, but the AI model makes forecasts that honestly look too good to be true because it almost perfectly matches the true cyclone. So after some time, now code has also become available to use these models. So not to train these models, but at the very least to use these models in some sort of inference step to make forecasts. And that's what we have been doing. So you can see the link in the bottom. So we have a KIT weather web page where we are running the Pengu weather model every day. So quasi-operationally started from initial conditions from a physics-based model. So the German Weather Service has essentially all their data available as open source data. So you can go ahead, download their initial conditions, and then run your AI model based on those initial conditions. And that's what we did here. So on the left-hand side, you can see a forecast from the AI weather model, started from the operational initial conditions of the German Weather Service. On the right-hand side, you can see the corresponding forecast from the German Weather Service. So these forecasts, I downloaded them, I think, Sunday evening, and they would be valid approximately now. And you can see that they look very similar. It's not exactly identical, but the overall shape of all these curves and colors looks similar. Maybe the physics-based model has a bit more fine structure detail. But what we can now do is we can actually compute how much this would cost us to do. So assuming you have a supercomputer somewhere in your basement, like we have at KIT, and assuming that we just have to pay electricity for that supercomputer, we can compute what it would cost to produce 1 year of forecasts. And we assume that we do it the same way the German Weather Service does. So we run 2 model runs per day. We produce 40 ensemble members for a global forecast every day of the year. Now for the physics-based model, this would cost us about 440,000 euros, which is pretty much exactly the price of a single-person home in the US on average. Now, of course, the interesting question is, like, what would this cost with an AI model? So maybe some people want to venture some guesses, so just shout some numbers at me what you think what this costs for a 1 year forecast in euros.
A Lego house?
A Lego house, yeah. Depending on a Lego house. Yeah. That's a good guess, actually, because this would just cost 200 euros. So that's like orders of magnitude cheaper. For forecasts that have, at the very least, the same quality, that are maybe even better. So this is just for running a model in an inference mode. So this doesn't include model training, of course. And it's difficult to assess what model training would really cost because we don't have code to train the model. So we can't run training runs ourselves. We have to trust what these companies state in their papers, but if you trust those numbers, then you would end up with a number like 10,000 euros for training these models.
One model, the final model, or all the models?
Well, that's what they state in their paper. Right? They argue specifically for this Pangu weather paper, they just did this once. Right? And then they even didn't finish training, they just stopped because it got too expensive at some point to train the model further. So trusting these statements, you end up at 10,000 words. But even if you do this 10 times, you are still far away from the physics-based weather model, right? So one question that, of course, we are interested in is whether we will be out of a job now, because what happens if in 5 years all weather services just run AI models? So do these AI weather models still benefit from post-processing? So that's sort of the one-slide summary of this. So the answer is yes. The answer is actually a bit more complicated, because all these AI weather models for now are just deterministic models. So in the end, we have to figure out a way how to turn them into probabilistic models. The blue lines are different ways to turn this Pangu weather model into a probabilistic model. The red line you can see is the ECMWF model, so again, the physics-based ensemble model, and the yellowish lines are two different post-processing models, where we post-process now the Pangu weather forecast, not the physics-based weather forecast, and you can see that here for 2-meter temperature forecasts over Europe, you can see CRPS versus lead time in hours. You can see that it's actually important to apply this post-processing step to be able to outperform the physics-based model. So to summarize this last part and the whole talk, I think there is like surprisingly tremendous progress, particularly in these AI-based models over the past 2 years alone. These show very good forecast skills, so they will be here to stay. But for now, it's also important to note that they can't replace the physical models yet. So the reasons for this are a little bit more complicated and technical, because these AI weather models, they need forecasts on the 2D grid to then produce, or they need sort of initial conditions on the 2D grid to produce the forecasts. And to produce these initial conditions, we have to sort of collect data from satellites, from weather stations, from airplanes, and so on. And to turn these observations into gridded initial conditions, this involves the physical model. So for now, you still need a physical model to be able to then run your AI model, so as of today. So probably many people are working on how to get rid of the physics-based model in this step as well. So there has been progress, but there are many open questions. For example, will these models work in a changing climate? They are trained on data from the past 50, 60 years. What happens if the climate changes? So we have a sort of shift in the distribution. Will they still work? And as I told you, they tend to be deterministic forecasts only. So how do we get to probabilistic forecasts? And then maybe not so much problem if you work in private industry, but as a researcher at a university, seeing that many of these developments now come from private industry and are driven by private industry without having code available to really understand what's going on, this of course, I think leads to the question, where does this leave university research? And what can we do to improve our understanding and of the potential limitations really from a research perspective? So, yeah, with this, thank you for your attention, and I'm happy to answer questions.
So, any questions? We can just take this microphone, and you just need to stay next to the computer.
Thanks for the talk. I would be curious to understand, or get your best guess, if you compare the AI model with the AI post-process model, and to say, okay, it's even better. Where's the signal coming from?
Yes, so to be fair, what we compared here was the AI model versus the physics-based model without any post-processing. So the interesting comparison is what would happen if you compare the post-processed model and the AI model. We didn't do this here because we didn't have enough data, because getting a past data from these physics-based weather models on a huge grid is very costly in terms of time, because the download speed are extremely low and the weather services don't provide the data in the fastest way possible, naturally. So we have done some small experiments, and I think in the end, the forecast quality will be about the same. So if you compare AI plus post-processing versus physics model plus post-processing, will be about the same.
Behind the jungle there. Behind the plant.
Thanks for the extremely nice talk. I had a question about actually
So you compare a lot with like physics-based model, and I think very recently there was actually a Google paper on it's called like neural GCN, I think, and that like I think the interesting stuff for me was that they used both a graph neural network but also a differentiable physics simulator. And I think the differentiable part actually contributes a lot to the speed up that you have kind of naturally in a neural network but not in a physics solver. Does this enter your research in some way, or like do you have opinions on like these sort of approaches?
Yeah, I think that's a very interesting approach, and I think that's one of the very interesting ways forward, because this also enables, for example, the step towards climate modeling. I think in the new GenAI paper, they also show that you can run this model in sort of a climate setup, but you can't really do in this purely weather forecasting models, because then forecast errors will accumulate if you run this sort of auto-regressively. So I think that's very interesting, and yeah, as I said, I think that's the way forward. In terms of forecast quality, I think for now, for these timescales that I showed, the new GenAI model is about the same quality as, say, the Pango weather model, and after post-processing this will be the same. But I think it's also, what they also do is, I think that was the first paper actually to make this step towards probabilistic forecast, so they have some sort of stochastic component in their model, so I think that's a very interesting development. And I think that will definitely be one of the ways forward, also to get to probabilistic models that are AI-based in data.
Thanks. We have two more questions in the last row, I think. Then one more question in the last row.
How's it with the forecasting of unprecedented climatic events?
Yes, that's a good question. So there are some studies specifically for these AI weather models on whether they can produce events that have never been observed in the training data. And I think the initial hope that you would have is that a physics-based model should be much better at doing this, because it's modeling physics in principle, so it should be able to extrapolate beyond what it has seen in training, because it's not really trained, but it's just like physical equations. And you would expect that the AI model is not really good at doing this if you try to predict something outside of the training data. But what these studies have shown is that actually this is not really the case, and the AI models are about as good as the physics model in predicting unprecedented events. For example, there was a heat wave in the UK with temperatures of 40 degrees that have never been observed before. But if you look at forecasts started at the same time, then the physics-based model performs about as good as the AI-based weather models. I think that's something that's not really well understood, because that's also maybe not what people expected. But there's now lots of research going into this and trying to figure out what's going on and where the limitations are.
Okay, I think there's one last question. One last question.
Can you thanks for the talk. But can you maybe, or do you have any special guesses why the interest in from these private companies into weather forecasting has risen in the short past? Because transformers have been there since 2017. Of course, GenAI hype is only there since November last year or before, but any guesses?
Yes, that's a very good question, and we have of course been wondering about this as well. So we have some contacts to people there at Google and so on. So I'm not sure. So I don't know. I think there are different aspects to this. So one aspect is that I think this is recognized as a very hard scientific problem to do weather forecasting, and maybe just showing that you are the best at solving this problem and at doing this is important or interesting for these companies to show that you have the expertise of doing this. So I think that that's one component, to show that you are the best at solving a complicated problem. But on the other hand, weather is also a pretty big business. So people pay lots of money for weather services. So one option for those companies is also to sell their weather forecasts. Maybe that's also one of the reasons why none of these codes for all of these models are really open source. So you can just run the model in inference mode, but you can't really train the model. And maybe there's a reason why that's the case. So maybe these companies also want to sell their weather forecasts somehow to the public, or to users of their smartphones, or to the weather services back. So that's also an option. But I don't know, so it's just speculation.
Thanks. So I would say another warm applause for Sebastian. Thank you. And I think besides that, Robert mentioned already, next meetup is scheduled already, so let's foster this community. I really liked now also going a bit deeper into formulas and another field, because we always talk about weather. All our clients want weather, and we still don't know yet how big the impact is for demand and sales forecasting, for example. But to get a view of the other side, how it is to produce such a weather forecast, which we would need. So thanks a lot. And yeah, the bar, and I think there are 4 slices of pizza there. Feel free to stay a bit, and otherwise hope to see you soon all, and happy discussions. Thank you for being here.